So 61 is how many valence electrons are in each element. That means we're going to go find the element and its group number, right? So oxygen is in group 16, right? If it's in group 16, it has 6 valence electrons, right? Everything in that group has 6 valence electrons, right? Sulfur, oh my gosh, same group, also 6. Bromine, right here, has 7 valence electrons, right? And that should always be really easy because we know that this last group, with the exception of helium, all have, right, 8 valence electrons, where 8 valence electrons is the number to be stable, right? And finally, we've got rubidium, which is in group 1, which has 1 valence electron. Then that brings us to number 65, where we're supposed to be able to use the periodic table to come up with the electron configurations, right? This table doesn't have it, but here are our period numbers because we need those, obviously, right? So let's go ahead and practice a few together. So aluminum. Aluminum is right here, right? So if we think about what that means we've passed this, right? So we've passed 1s2. We've passed that, which would be 2s2. All of that, which would be 2p6. 2 more, so 3s2. And then here, so we are 1 into the 3p's, so 3p1. Yes? All right, now for beryllium. If we go find beryllium, beryllium is right here, right? So same principle. We've passed those, so that's 1s2. We've passed those, oh, so 2s2. That's it, right? If we're going to do indium, right, we'd have to go find that one first, which is right down here, right? But same principle, right? We've passed all of that, right? So that's 1s2, 2s2, 2p6, 3s2, 3p6. And then we've done 4s2, right? And then we got to remember that this is back 1, so 3d10. And then here, right, we go back to the valence, so 4p6. Then we come over here, that's 5s. And then we got 4d, because d's are always going to be back 1. And then 5p1, right? Because for our main group, right, because remember we've got our main groups. For our main group, which is groups 1 and 2, and 13 through 18, right, that's where we have our S and P's, right? Those generally make up our valence, right? So we've done indium. And then for zirconium, same thing, right? We would go find zirconium, which we did that one the other day. Zirconium's right here, number 40, right? So we would do the same thing, right? What have we covered to that point, right? So to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d2. Yes? Does that make sense? All right. Now, that means 67 is just like 65, so you would just follow that pattern. The only one that might be different is the F ones, but we practiced that the other day. Number 69, how many 2p electrons are in an atom of each element, right? And again, this is something that we can glean just from looking at the periodic table, right? So if we take a look at our periodic table, and we wanted to do carbon, right? So first, it works the same way. Let's go find carbon, right? So carbon is right here. And we want to know how many p electrons. Well, how many into the p block is it, right? So it's 1, 2 into the p block. So it has 2 p electrons, right? Nitrogen, same thing, right? We would go find nitrogen is right here. And it is 1, 2, 3 into the p block. So it would have 3 p electrons, right? And so forth and so on, right? The process would repeat, okay? Now, the only tricky one would be that phosphorus, which is not even really tricky, right? But phosphorus is down here. And the question actually asks how many 2p electrons? Well, 2p would be these, right? And since phosphorus is beyond those, it would have all of them, yes? All right, then that brings us to number 73, where here now we are just, again, taking what we know from the periodic table and answering some questions, right? So it says we want the one that has, so it says we are in the third period, right? So let's count down 1, 2, 3. So we're in this period. And it says we want to find the one that has 3 valence electrons. Well, then that means we would count, right? 1, 2, 3. 3 valence electrons, that's aluminum, right? a total of 4 3p electrons, right? Well, if we want 4 3p electrons, we would count 1, 2, 3, 4 deep into the p block, right? The one that has 6 3p electrons, right? Well, then we would just finish counting and get to argon. 2 3s and no 3p, right? So 2 3s and no 3p. Well, that would just be, that puts us right here at magnesium, yes? That has 2 3s electrons and no 3p electrons, okay? Number 75 is similar, right, in that we're just going to take what we know and find them, right? We're just going to use the periodic table as a map, right? So A says neon and then 3s2, 3p5. So 3s2, past there, 3p5. 1, 2, 3, 4, 5. Chlorine, right? Next one says argon, 4s2. So argon, 4s2. So let's go 4s2 and then 3d10. So we're going to pass all of that. And 4p1, gallium, right? The next one says argon. So let's erase that, right? So it says we start from argon, 4s2, and then 3d6. So 1, 2, 3, 4, 5, 6. Iron, right? And then we have krypton, 5s1. So krypton, 5s1, rubidium, okay? So basically, it's like a board game with the periodic table. All right, for the periodic trends, so number 77, 81, and 85, all we're doing is employing what we talked about in the previous lecture, right? Where we have our set of trends that's based on where things are located on the periodic table and their electron configurations, right? So if we think about number 77, it says the higher ionization energy. Well, IE increases this way, right? So things that are further to the right have a higher ionization energy, right? Or what else? Right, this way. IE also increases that way, right? So things that are further to the right or things that are higher up will have the higher ionization energy, right? And then it says choose the larger atom, right? So larger goes with atomic radius, right? So if we go in this direction, right? Radius decreases and radius decreases. Yes, as in radius decreases as we go to the right, radius decreases as we go up. And then finally, that brings us to metallic, right? As we go to the right, metallic character decreases, right? And metallic character decreases as we go up, right? And whether you want to memorize it the other way is fine also, right? We could memorize it. You just need to be clear when you write your answers, okay? Number 93 asks us to write the electron configurations for each of those ions, right? So obviously, this one's a little bit thoughtful. If something is a cation, right, like that Ca2+, right, what happened to it for it to become a cation? Right, that means it lost electrons. So if it lost electrons, that means we would have to think about how many calcium came with, which would be 20, right? So calcium comes with 20 electrons, which means calcium 2+ must have, right, 18 electrons. So once we've deduced that, now we just write an electron configuration for 18 electrons, right? So that'd be 1s2, 2s2, 2p6, 3s2, 3p6, what is that, 10, 18, right? So now we're done. Yes, does that make sense? And then if we look at, let's look at S2-, for example, S2-, in order to become an anion, what happened to it? Right, it gained electrons. So if we look at normal S or neutral S, that has 16 electrons. In order to be S2-, it now has 18 electrons. What? That means its configuration looks just like, oh my gosh. So actually, everything A, B, C, and D of 93, that whole set is referred to as isoelectronic, right? Meaning that they all have the same electron configuration, right? So things that have the same electron configuration are referred to as isoelectronic, right? Number 97 is just applying your rules and figuring out what's wrong, right? So if you look at 97A, right, can P's have 9? No, right? Can S's have 3? No. All right, so I just wanted to make sure you have a little bit of explanation to go with your answers since I am not there for you to ask me questions. All right, thanks for listening, be good, and I will see you next class period. All right, bye guys.